Good morning and welcome back. We were discussing the IV characteristics of a MOSFET. And while doing that, we obviously will have to take into account the fact that the structure of the MOSFET is of a certain type. So we call this stuff on here gate. This is body. One of these terminals we can call source, the other terminal drain. By the way, a question for you. This is a physically symmetric structure, right? Whatever, I mean, there is a line of symmetry on either side of it. So how do you determine which is source, which is drain? I mean, these two, I could have as well called this to be drain, that to be source. And looking at the structure, you wouldn't have made any difference, right? So how do you ascertain which of these two terminals will be source or drain? No, body is also common to both terminals, right? It doesn't matter. Right. What it says is that it really doesn't matter. It doesn't matter because ultimately, what is the how are you getting carrier flow? So firstly, you'll have to obviously apply certain voltage between, let's say, gate and body. Okay. Then it creates some carrier in the channel. Now, depending upon how you connect the battery between drain and source, right? So if I connect a battery like this, then the current will flow left to right. And if I connect a battery like this, the current will flow right to left. So the drain and sources are interchangeable. Whichever is the higher potential, essentially, in this particular architecture is the drain. And whichever is the lower potential is the source. Note that if you have you had some preliminary introduction to BJTs in ESC 201. In a BJT, you cannot do this. It's basically the structure of a BJT is as is. If you reverse the collector and the emitter, you can as well mark one as emitter and the other as a collector, or BJT will not work. But in this case, a MOSFET device, it really doesn't matter. Your source and drains are interchangeable, and how is it interchangeable? The one that is at a higher potential is the drain, the one that is at lower potential is the source in this particular type of MOSFET. Okay. Another terminology is the fact that we started off saying that this is a p-type semiconductor, and the charges that are giving rise to carrier transport in this channel are electrons, right? Because we initially applied some voltage between gate and body, and we drove away the holes, and we kept on driving them away till we had mobile electrons. So the carrier transport in this device is being facilitated by electrons, which is essentially N-type. So we call this particular device as NMOSFET, NMOS. Okay, this is an NMOS transistor, or it's called NMOSFET. So obviously, it naturally follows that if we have an NMOSFET, there will also be a PMOSFET, right? So we'll get to that later. Okay, so now then we said that, okay, I also again made a further point that in the presence of these drain and source dopings, which are N+, you may as well get rid of this body terminal to, you may as well refer the gate voltage to the source terminal, because now you have a locally placed high concentration of electrons, right? When there is a need for electrons, these N+ regions can supply the electrons. You did not wait for thermal generation to take place. So which essentially means that I can simply refer everything to source, right? I can refer everything to source. And for this example, let's assume that the source is grounded. And let's also assume that the body is also grounded. The only constraint that body needs to satisfy is to ensure that the PN junctions that has taken place because that has formed because of this N plus P minus doping is reverse biased. Because if it's forward biased, all the current that I expect that I want to all the carriers that I want to make flow, all the carriers that we want to flow from source to drain or drain to source or whatever through the channel will not flow through the channel. It will go through the forward bias PN junction. So essentially, you have to ensure that by virtue of your voltage choices, these drain to body junctions or drain source to body junctions are always reverse biased. That is a design choice. That is your responsibility as a designer. Yes. Okay, so it's not necessary that you have to connect it like this. So I can always say that I have a battery between these two and I have a battery between these two. Right? Which battery? Between gate and body, are you okay with the fact that we need a battery between gate and body? But also you will have to, ultimately when you are designing any circuit, there is only one reference node, and with respect to that reference node, you have to define the potentials of others, right? So if we simply say that I will make this a floating battery per se, then can you make a comment on what is the exact voltage at the source or the drain? I know the difference between the source and the drain is certain, whatever battery I have applied between it. But there is no way for me to ascertain whether the source is at a certain potential or the drain is at a certain potential. If I cannot ascertain that, then I also cannot ascertain whether my drain body junctions or drain source junctions are reverse biased. So it's up to luck. We don't want luck to come into picture here. We have to ensure that everything is defined. So one way to define that is to say I will refer everything to certain body. That means that I can as well say that let's assume the body is of a certain voltage. In this case, let's assume to be referred. Let's assume it to be a ground. So I will refer this to a source and refer this to this, and let's assume this to be ground for the time being. It's need not necessarily be ground. It can be any other potential also. But for the purpose of this discussion, we can refer it to. Yes. Okay. So let's assume for the time being that this junction is forward biased. Right. So maybe you were not careful enough. You had a battery where you had given a positive potential to the P-type, right, during design. This is in your control. So now, because of that, what will happen? This junction becomes forward biased, or maybe this junction becomes forward biased, can likely become forward biased. So if it becomes forward biased, then the carriers will flow directly from the body to the channel to this, right? So this entire current flow loop will now become this through the body and back, right? You don't want that because that loses the MOSFET action. MOSFET action is based on the fact that you are inducing a channel and you are controlling the channel. And if you completely bypass the channel, it becomes a resistor. We would not have control of it. Right. So only way you would want, essentially you would want all the carrier transfer to take place through the channel. It's a pipe. You want it to flow through the pipe. You don't want the pipe to leak. So this is the leakage, right? So you don't want that to happen. So that's why you would want to ensure that all the PN junctions which you don't want to be forward biased should be reverse biased. Okay, now coming back to the question that let's have a quick discussion of what is the current voltage relationship of this drain between this drain to source. So now, if you have a certain VGB or VGS in this case, so this is grounded. Let's assume that you have certain VGS So what is the channel? What is the carrier, mobile carrier concentration in the channel? Using the concept of threshold voltage, what will be the mobile carrier concentration in the channel if you have applied certain VGS? So it will be VGS minus VTH is so this is Q mobile. Should be proportional to the voltage that you have applied between the plates. It's a capacitor. Should not surprise us that the charge in the capacitor is proportional to the effective voltage. Now this is the effective voltage because threshold voltage went in essentially driving holes away and getting to inversion. Beyond inversion, you have mobile charges. Now, since you have mobile charges, the effective threshold voltage will essentially give you the mobile charges that can give rise to carrier transport. And we are interested in the carrier transport. Note that this is not the total charge. This is only that charge that is giving rise to carrier transport. Right? Since this is the only that charge that is giving rise to carrier transport, this is what that will play a part in our IV characteristics. And this is essentially proportional to the effective voltage that you have applied between the gate and the channel, which is VGS minus VTH. And you have voltage, you need charge. What else do you require? In a capacitor, you know the voltage, you need charge. What else do you require? Capacitance, right? So that is C oxide. You can do VGP also, but the argument that I made was why did we start off with VGP? We started off with VGP because we said that if we have the excess electrons we are getting because we have thermal generation, right? So thermal generation is kind of a slow process. It takes longer time in terms of its time constant is, I don't have a number right now, but its time constant is not very high. But now if you have a doping like this N+ dopings on both sides, then you essentially have wells of electrons sitting there. Whenever there is a requirement of electrons in the channels, these wells of electrons can supply them. Your device doesn't need to wait for the slow process of generation to get those electrons, right? So essentially, if all the supply which was coming from thermal generation is now coming from source. So that is why you can essentially refer all these voltages responsible for creating charges in electrons in this channel to source, right? And the purpose of body essentially relegated to ensure that everything is reverse bias. Okay. Okay, fine. So this C oxide essentially is, I mean, I can express this C oxide in terms of unit oxide capacitance times the area, right? So if I look from the top, this is a cross section, right? If I look from the top, essentially you will get this is L, this is W, and this is probably the channel underneath, right? The channel underneath where you have applied, this is VS, this is VD, this is VG. So if I look from the top, I'll get the oxide will be Cox times which W times L. Well, Cox is the oxide capacitance per unit area. Okay, so that which means that I can replace this with Cox times W times L. So now we have charges, mobile charges in the channel. I need to figure out what will be the current, right? So how do we figure out current? So the current is, I mean, we are getting current in this channel because these charges are moving, and charges moving at a certain rate gives us a channel. How do I get charges moving at a certain rate? This is Q mobile by the time it takes for these carriers to move from, let's say, drain to source or source to drain, regardless of, I mean, whether you're talking about positive charges or negative charges. And what is tau? Tau is the I call it drift because you have to be slightly careful in semiconductor. There are two types of carrier transports. This drift velocity is equivalent to, in terms of device dimension, is the length that it has to travel divided by the velocity. What is the length? This is L by the velocity. And also, what is the velocity under the influence of an electric field? Mu times mobility times the effective electric field. So this becomes mu times electric field between drain and source. So you have an electric field here. And now what is the electric field in terms of voltage and distance? V by L, right? VDS by L, which means this becomes L squared by mu n times VDS. Now we plug this into the current equation, which means this becomes VGS minus VTH. C ox. Well. So algebra leads to okay. So see, from the first principles, we were able to come to a current voltage relationship of a MOSFET. And this is good. This is an abstraction, but this is good. We don't have to worry about how people doped it, right? What is the, what is the structure of the MOSFET? Obviously, at the back of the mind, we need to have that information of how it has been doped, what is the forward bias, what is the reverse bias, certain junctions. Those assumptions are always, we should always have at the back of our mind. But this is the power of abstraction, right? We can say that, okay, some people have given us the devices, put in a lot of effort. All I want is a current voltage relationship between the ports that I am interested in. And this gives us the current voltage relationship between the ports in terms of the variables of interest. It's not only sufficient to get the current voltage relationship. If you are a circuit designer, you need to know what are the knobs you can control. And what are the knobs? The knobs are voltages and also certain aspects of the device dimensions. So in this case, the knobs that you have is VGS, VDS, and W by L. Right? The width of the transistor, the length of the transistor, the voltages that you have applied between different terminals. And why is that? I mean, intuitively, why should this make sense? It essentially is telling you that if you have higher VGS, if you fix VDS, and if you have higher VGS, looks like you will get more current. Why does it make sense? Does it make sense? Yeah. And why does it make sense? Because the flow is being determined by VDS, right? VGS, what is the purpose of VGS? VGS is generating carriers. VGS is generating carriers in the channel, right? The amount of VGS over threshold voltage is responsible for generating carriers, and VDS is essentially pushing the carriers, right? So flow is being determined by VDS, and the generation concentration is determined by VGS minus VTH. So that is one of the reasons. I mean, so not that is one of the reasons. Essentially, this is called this term is often called V overdrive, VOV. It's overdrive because if VOV is 0, that is VGS equal to VTH. By our model, we are essentially saying that there is no carrier, no carrier to flow. If you have no carrier, no current. So OV means overdrive. How much you have driven the gate on top of the threshold voltage in order to generate the carrier. And VDS is obviously the force that you are applying between. It's a representation of the force that you are applying between drain and source terminal, which in terms in this case is a voltage. Yes. Does that also translate not necessarily, because in fact no, because you are saying that does that mean that if I have more VGS, this green region will increase, right? Right, because ultimately what is happening, if we didn't have any mobile carriers, then what you are saying would have been right. Because here we are having is everywhere I have Na plus, Na minus, H plus, right? So similarly, in the channel also, I have Na minus and H plus, but the H plus got driven away. H plus got driven away, and we are left with Na minus. If we are only being left with Na minus, if I increase VGS, then I'm increasing the concentration of the lines of forces from top to bottom, right? So these lines of forces, electrical lines of forces would have increased, which means for each extra lines of force that you incur, there should be a negative charge in the channel that has to get exposed. And if we didn't have any mobile carriers, if we only had Na minus, there was no other way for it to get exposed other than increasing the thickness of the channel. But now we are having mobile carriers. Because we are having mobile carriers, the extra lines of forces are getting terminated into the mobile carriers, and it's no longer required to increase the thickness of the channel, right? Good question. Okay, fine. So now we are circuit designers, so we'll have to now get back to our Y parameters, right? So note that a quick recap. What was the required IV characteristics for a two-port network for us to get amplification? Y21 should have been high, and Y22 and all the others should have been 0, right? So which essentially means that if I plot these 4 curves, I1, V1, so in this case, where what was I1, by the way, I'll have to first define what is I1, V1, otherwise things will become confusing. So let's assume that so this is the oxide, right? So this these parallel lines are essentially giving you the is pointing to the fact that there is an oxide in between. So this is an oxide. So this is equivalent to. So let me sketch this also. So this is an oxide here. So this gate corresponds to this gate, this terminal corresponds to drain, this terminal corresponds to source. And you have a body, but let's ignore body for the time being. You had a question? Okay. So that arrow indicates the direction of current flow. Okay. So this here, where is the the electrons are flowing from source to drain, but the current is flowing from drain to source, right? So this arrow in this case indicates the fact that I have some current between drain to source. Note that this device is physically symmetrical, right? So if, for example, if I had applied a voltage between drain and source, and assuming that you have sufficient VGS, current would have flowed from top to bottom. But if I had simply reversed the battery, right, the current would have actually flowed from bottom to top, right? But in that case, this arrow should have been flipped, right? This arrow should have been flipped, right? So, so that is why you have to be slightly careful while dealing with MOSFET. Okay, so it's not because I have an arrow somewhere, it means that that is a source, because source and drains are interchangeable. Okay, fine. So now, so if let's forget about the body for the time being. So let's say this is a 3-terminal device, and I put a port around it. I put a box around it, and I say that my port 1, the port 1 is between gate and source. This is 1 dash. So this is V1, let's say, and port 2 is between drain and source. Okay. And let's say this is I1, this is I2. So under these conditions, what do you think will be this I1, V1 characteristics? If I increase V1, that is, I'm increasing VGS, what will be I1? By the way, I mean, what is I1? In the examples that I showed,
Gate to body.
yeah, but is there a current between gate to body or gate to source? No, right? So I1 is 0, right? It's absolute 0, right? This is the best you can have. So I1 is 0, right? Condition 1 satisfied. I1 is 0 means Y11 has to be 0 also. What is this third plot? I2 V1. Sorry. No, let's not go there. Let's go to the second one. What is I1 V2? 0. Great. Right? So far, so good. What is I2 V1? I2 V1 will be linear because V1 is essentially in this case VGS, right? V1 is VGS. So V1 is essentially V. Pardon? Tell me. Looking at the structure, tell me. Yes, right? Where is this? Where is this I in this structure? What is this I? Is the I flowing from drain to source? In this 2-port, the current between drain to source is I2. So that I is I2. Okay. So now what will be this I2 versus V1? V1 is VGS, right? So all we have to do is look into this equation and make a judgment. What will that be?
Draw a VTH point on the
right. I have to draw a VTH point here.
Then
it goes linear. Perfect. And below VTH, our model is not valid, and we said that below VTH we cannot have any current. So essentially, it's flat. So this is good, right? If this is I2 versus V1, what is Y21? What? Right. So slope of this. So what is the slope? So this gives us Y21 also. What is Y21? Mu n Cox VDS. Great. So seems like okay, and we're in the right track till now, right? Yes. We'll get into that. We'll get to that. Right. So by the way, why do you say IT is saturated? Okay, we'll get to that, right? So something very interesting happens. So let's assume that this model is valid, right? If this model is valid, looks like I21 is what we want. Now come to I2 versus V2. What does I2 versus V2 looks like? Straight line from origin. Great. So straight line from origin, and this line is. So what if this is straight line from origin? What will be Y22? Great. So in our amplifier, what should Y22 be? It should be 0. Ideally, it should be 0, right? If I go to the 2-port network, if I go to my 2-port network, this was my Y11. Y11 and Y21 were 0 anyways, forget about them. This is Y21 V1. This was Y22. And you had a GL, right? You would wanted all the Y21 V1 to go into GL. If there is an Y22, you are losing. You are losing amplification. So you want Y22 to be 0. So the internal characteristics of the device is generating an Y22, right? The internal, this is not a physical resistor, right? This is not a physical resistor. This Y22 is, we are getting an Y22 because the device has certain structure, has certain way of operation. So this, because of this Y22 is not 0. So which means that under the condition that we are looking at, this device cannot be used as an amplifier. Make sense? But note that this device can be used as a resistor. This I2 versus V2 characteristics, what is it telling you? It's basically telling you that I2 versus V2 characteristics is a straight line, it's a straight line with a certain slope. And the slope essentially is the inverse of the slope is the resistance. It's a straight line and between the same ports. between I2, you apply some voltage V2, you are getting some I2, and the relationship between V2 and I2 is a straight line, which means it's a resistor. Great, but what's so fancy about this resistor? The value of this resistance is dependent on VGS minus VTH. The value of this resistance is dependent on some other voltage we have applied at some other terminal. It's a controllable resistance. It's a controllable resistance, and this control terminal is somewhere else. Right? That's why it's called a trans resistor, and hence the name transistor. Okay, it's a trans resistor, and hence the name transistor. So in fact, this configuration is often used in circuit design to get a voltage variable resistor. This is a voltage variable resistor, and the variable of interest is somewhere else. It's not between the terminals between which you have applied the voltages. So it's not the value of the resistance is not dependent on VDS. The value of the resistance is dependent on VGS, somewhere else that you have applied the voltage. Make sense? Okay, great. So now coming back to his question, what happens if I keep on increasing VDS? Will the current keep on increasing? Right? So obviously, I mean, you know that it's not going to happen, right? For whatever reason. So let's see what is the reason why it might cause a problem. So if you would have noticed, you would have seen that I probably cheated a bit. What did I do? I said that this channel has been found by somebody else. Then I have applied a voltage between drain and source, and there is a current that flows. That part is not cheating. The cheating was the fact that I assumed that I assume certain type of channel charge, profile of this channel charge. I assumed a rectangular profile of the channel charge. Right? I assume that when you applied a drain to source voltage, the channel charge remained rectangular. Right? I didn't assume that the channel charge might have changed because I assumed it to be a slab of charge. Right? I assumed it to be a slab of charge, where the concentration of the slab of charge is independent of the voltage that you apply. Right? Yes. I assume that the slab of charge is independent of VDS, but that need not necessarily be the case, because think of it in this way. Now I can look into this channel, and I can bifurcate it into small pieces, right? I can bifurcate into small pieces of channel. And if I zoom in here, each of these slivers is a small MOS transistor in itself. It's a metal on top, oxide below, and some channel underneath, right? So if that is the case, in order to figure out what is the concentration within this sliver, I need to know what is the voltage just underneath the oxide, right? Without that information, I cannot possibly figure out accurately what is the charge within that sliver, right? So if we have to do that, then obviously we'll have to take into consideration that there is a voltage profile along the channel. So let's take that into consideration. Let's say there is a voltage profile. You had applied certain VDS, so the voltage profile will probably decrease between maximum at the drain and minimum at the source. Even though I have drawn a straight line, it need not necessarily be the case. It can be any profile. All we know is that it will be maximum at the drain and minimum at the source. Okay, so let's just say that around a distance x from the drain, I'm interested in this lever. Yes. Okay, I have applied a battery. I have applied a battery between drain and source, and the positive voltage is at drain, and the minimum is at source, right? So just you are going from higher potential to lower potential, right? So at max, at best, it can be flat. It cannot go the other way around, right? So, okay, fine. So if I concentrate on that sliver and I say that this voltage here is Vx. Okay, So what is the channel charge within that sliver? What is the Q, dQ within that sliver? Obviously, you'll have to take capacitance, which is Cox times dx times W. I haven't shown the W. W is in the other direction, right? The slab has certain width. So times W times what? Vg minus VTH minus V of X. Right? Because the potential across the oxide is no longer Vg minus Vt. Right? It's Vg minus Vt minus V of X. Yes. V of X is the potential just here. So if you zoom in, you assume this to be a small transistor in itself, right? Then you would be interested in knowing what is the voltage at both sides of the plate, right? I assume that the voltage at the bottom side of the plate is V of X. Okay. Yes. It can be, but it not necessarily be, right? So what you are saying, yes, in fact, under this condition, yes, it is. But as it turns out, it's not because of some other second order effects, right? So I'll maybe refer to that later. Yes. Okay, so you are comfortable with this. And what about, why are you not comfortable with minus V of X? So note that this is Vt, right? I can assume that this is Vt here because everything is referred to, right? But we are interested in the charge here. It's a parallel shape, right? I know that, so I need to know that voltage difference between them. One, I know this voltage, I need to know this voltage. This voltage I am calling it a sliver. Right. So within that small sliver, I have that much amount of charge.
Does the maximum value of V of X is Vt, right?
Exactly. The maximum value of V of X is Vt, right? So let's, I mean, since everything is referred to S, let me call it VGS here in this case itself.
The reason you are doing this what happens is
if I keep on increasing, yeah, if I keep on increasing VGS, what happens, right? Okay, fine. So far so good. So I need to figure out also the current. Ultimately, we are after current, right? We need to figure out what is the current that is flowing through this sliver, across this sliver rather. I need to figure out what is the current that is flowing through this sliver. And under steady state, this current is constant regardless of whichever sliver you choose. There is no building up happening, right? So I choose any sliver, figure out the current, then I know what is the current through the device. All I need to know is to figure out what is the current through this sliver. So so what will be the current? It will be dq dt, dq d tau rather in this case, right? So it will be dq d tau. Fine. So what is dx d tau? It's basically the drift velocity, right? So this, so let me have the terms on the right hand side that will help with the algebra. So dx dt is essentially velocity. Velocity is mu n times electric field, right? So this is mu n times the electric field within that sliver, right? Within dx. So what is electric field? It's minus dV dx, where dV is the voltage across that sliver, right? So this E, this dx is subscript, by the way, right? Is minus dvx dx, right? All calculus and algebra, nothing to do with the device operation. So now if we know this, then this becomes current is equal to Cox W VGS minus threshold voltage minus V of X, mu n comes here, dVx, dx. Right? So I take the dx out over to the left hand side. So this becomes I dx. And now this is in your territory. You can simply integrate, right? I'll have to go minus. I had missed a minus somewhere, right? So this would have been minus. It would have been minus here. Now you integrate. Now current is constant, so doesn't come into integration. Doesn't. I mean, you can take it out. And dx, x varies from 0 to L, right? X varies from 0 to L, and Vx varies from
0 to VDS.
no VDS to 0.
Yes.
My x equal to 0 is this. This is x equal to 0, right? This is x equal to 0. So this goes from VDS to 0. So I times L is minus mu n Cox W VDS minus VTH times, okay, so this other term goes, so this becomes VDS minus half of VDS squared. Right? So in other words, the current is mu n Cox W over L, VGS minus VTH is VDS. Okay. So note that this becomes a better approximation of the current. So under the condition that VDS, under the condition that we could have neglected this term, we would have been left with this term, which was the 0th order approximation that we started off with. Okay, make sense? Make sense? Okay, so now we do the same exercise again, right? Find out IV characteristics. Again, I did not bother about I1, V1, I1, V2 because I1, V1, I1, V2 are at 0. MOSFET is a good device, right? So let's do I2, V1 and I2, V2. So what will be, sorry, I2, V1. I2 is equivalent to this I, is IDS, right? This is, I should, if I call it IDS, this is IDS. So what will your I2, V1 look like? For a particular VDS, what will I2, V1 look like? It will be a straight line again from threshold voltage. So it will be a straight line, right? Which is good. We still have, we can possibly get high Y21. So what will be Y21? Same, right? Mu n Cox W over L. What will you differentiate it with? VGS. So it becomes VDS, right? No change in Y21 with respect to the previous step, right? What is Y22? Or rather, let me plot I2 versus V2. What will it look like? Approximately, what does it look like? I mean, what do you think? It reminds you some, it's a parabola, right? So initially it will be, I mean, for very small value of VDS, I can neglect the half VDS squared term. So it becomes straight line as it was earlier, but after some time it will inflect. Correct? So after some time, after some V2, some VDS, it will inflect, start inflecting. Correct? But again, there is a catch. I'll go to the catch. Before I go to the catch, let's assume that we don't wait till it drips down. Let's concentrate on before you hit the maximum. Okay. So what will be Y22 for this expression? You differentiate with respect to VDS, so you get mu n Cox right? So see, it is still not 0, but I have been able to reduce it to some extent, right? If I increase VDS, right? Initially, under the previous approximation, under the previous model, I only had VGS minus VTH, right? If I have to reduce Y to 2, I have to reduce that VGS minus VTH, whatever is giving. If I reduce it to 0, right? If I subtract some amount from VGS minus VTH and make sure that whatever I am subtracting is exactly equal to VGS minus VTH, then I can get to Y22 equal to 0, right? So the moot point is that it seems like Y22 is flattening out, right? Y22 is going to 0. The IDDB characteristics, IB characteristics is flattening out. It looks like we are going to where we want. We are at least in the right track. Whether we'll go there or not is a different story, but we are on the right track. Yes. You differentiate with yeah, in Y2, right? So, okay. Yes.
VGS, right?
No, V2 was what? V2 was VDS, right?
VDS.
Right? V2 was VDS. Okay. So far so good. Now let me bring you back to. Now let's we are in the right track, but let's assume. Okay, so what happens when VDS is exactly equal to VGS minus VTH from this model? What does Y22 look like? It goes to 0, right? So it looks like we are in the right track. So we have to see what happens to the device when VDS becomes exactly equal to VGS minus VTH. So let's go there. Let's go there. So this is gate. So by the way, when we applied a potential, in this case, right? In this case, what do you think will the channel charge look like will it still look like rectangular? It will go tapered because note that the concentration of the charge, in this sliver, if I compare the sliver on the right with the sliver on the left, right? So what will be the effective voltage? Can you comment on the effective voltage across the oxide between these two slivers, the sliver on the left and the right?
More on the left.
More on the left, right? Because the gate voltage is constant for both those slivers, but thus the channel voltage here is lower than the channel voltage here. So you expect more charge, more mobile charges on the sliver on the left than on the sliver on the right. Right? So and that if I somebody else is listening. Okay. So if I extend that argument, then it makes sense to say that instead of having a rectangular charge distribution, I'll probably have a charge distribution which looks like this. The details of it is a matter of currents and voltages and charges and blah. But you have to, we should agree on the fact that, I hope you agree on the fact that it will be something trapezoidal.
Can you please, how did we get this then?
Okay, so how did we get what? Okay, so if I concentrate on the charges in this channel here and the mobile charges underneath here, where do you think the mobile charges will be higher? Right? So mobile charge is a function of oxide times the voltage across the plates. Oxide is same for those slivers. Gate voltage is same for both those slivers, but channel voltage is different, right? Because channel voltage had tapered from drain to source. So the channel voltage here was higher, right? So this, let's say this is Vx and this is Vy, right? So obviously you can say that Vx was greater than Vy. Right? So this is simply by observation, right? If Vx has to be more than Vy, then obviously the charge that accumulated under the oxide at X should have been no, Vx is greater than Vy, right? So the charge the voltage profile goes like this. You have higher voltage here.
So this being negate electron.
Which one negates? It's not negating, right? Why should you say it's negative? No. It only indicates the amount. I am trying to motivate is that what will be the charge under that sliver. If I see the current flow is a function of two things. You need to have charge and you need to have field. Now, because I have a trans effect, right? There is the charge is getting generated by the vertical electric field. I need to figure out what is the concentration of it. Right? So the concentration of charge here will be more than the concentration of charge on the green line will be less because the voltage here will be higher, right? Because the voltage here is higher, the difference of voltage is smaller, right? So which means you have lesser charge here than on the blue, right? So give me one more minute. So what happens when VGS minus VTH becomes VDS? What happens at this junction? So note, I'm now trying to concentrate what is happening here, right at x equal to 0, right? What happens then? This I can as well say this is equal to VG minus VS minus threshold voltage is equal to VD minus VS, right? This goes, which means that I am saying VGD is equal to threshold voltage, right? So now if VGD is equal to threshold voltage, which means what? What is the concentration right at that edge? 0. It's 0. The channel is vanished. Channel is pinched off. We call it pinched off condition. Channel has pinched off. Okay. So we'll see in the next class that as it turns out, when the channel becomes pinched off, there is, even if you apply more and more VDS, you will not get any excess current. The current saturates. And why is it important? If the current saturates, you get Y22 equal to 0, right? Great. That is what we were after, right? So we'll see that in the next class.